Welcome back to Chips and Salsa, where we talk security at Intel. I'm Jerry Bryant. Our topic today is formal verification at silicon scale. Joining me is Senior Director here at Intel, Jason Fung, who, you run offensive security research and academic research engagement. Thank you for coming back on the show, Jason. It's good to have you here. Can you start by telling us a little bit about what your team does and a little bit more about this academic research engagement?
Great to be back, Jerry. My team proactively hack Intel products while they are still under active development so as to ensure we deliver trustworthy technologies that enrich people's lives. And we collaborate heavily with the academic research community. And these are some of the brightest minds on the planet. We meet weekly with top-tier institutions to learn from their latest work while sharing industry insights that help shape their research towards real-world impacts.
And Jason, I had a conversation with Vivek Tiwari about negative space testing, and he referred to hackers as bad actors.
It's not us.
I don't think Jason looks like a bad actor.
It is not us.
So, hey, formal verification, in simple terms, what is it and why does it matter to modern silicon security?
Formal verification uses mathematical algorithms to prove whether a hardware design meets its requirements under all possible conditions, and even for the rare corner cases. And if these requirements are met, it returns a pass. If they are not, it returns a fail, along with a precise counterexample showing when and why. And when applied to security requirements, formal verification delivers something we call provable security. And as you know, Jerry, many vulnerabilities hide in edge cases that traditional testing may never hit. And formal methods remove that guesswork by exhaustively checking all possible scenarios.
Excellent. So silicon complexity is increasing across commercial-grade SOCs for servers and client systems. Why has formal verification become indispensable now?
So modern SoCs integrate hundreds of unique IP building blocks that include multiple security engines, handling mission-critical security flows, dozens of microcontrollers with different instruction set architectures running programmable firmware, and many security-sensitive components requiring deep security reviews. And these leads to thousands of security properties to verify, and tens of thousands of sensitive registers, and hundreds of thousands of critical signals, all needs to be verified before tape-in. And traditional simulation tries to increase confidence by running more tests, but with today's complexity, it is virtually impossible to exercise every scenario in practice. And formal verification provides an orthogonal, exhaustive approach, dramatically boosting assurance without brute force testing.
So we've been doing formal verification for a while. What kinds of innovations has Intel made when it comes to formal verification?
Yeah, traditionally formal methods verify functional correctness, like checking complex state machines and protocols for deadlock or for race conditions. Intel has extended formal verification for security assurance, and back in 2020, we partnered with MITRE to create the Hardware Common Weakness Enumeration CWE as a taxonomy, and now with over 100 common hardware security weaknesses. And we have demonstrated how formal methods can effectively detect these hardware CWEs in various hardware designs. And we also built methodologies and tools to lower the barriers so engineers can apply formal without needing to be a formal or security experts. Today, Intel engineering teams use formal methods daily to ensure our IP building blocks are free of known hardware security issues.
So what sorts of issues, I know you kind of mentioned this, but what sorts of issues does formal verification uncover that traditional validation may not find?
So here are two classes I would call the high-impact security weaknesses that formal verification works particularly well to uncover. The first type is called information flow tracking. And taking AES Crypto Accelerator as an example, we want to find out whether the crypto material leaked through some output signals that are unintentional. And with simulation, unintended leakages are very difficult to uncover. And we need to predict precisely where the potential leaks might occur and specifically looking for them. And for formal methods, it can precisely check whether the sensitive data can ever leak through any unintentional path by representing the designer's intent in a simple equation, or we call property. And the mathematical engine will evaluate the constraints and provide an answer. And the second class of issues is what you and Vivek talks about. It's called the negative space testing. And I think the viewers can go back to the videos to learn a bit more about the detail, so I'm not going to go into exactly what it means, but as a nutshell, negative space testing verifies if a design handles malformed inputs and error conditions properly. And like software fuzzing, there are usually more simulation tests to run than available time, and leading to best effort coverage in practice. For formal verification, however, taking a white box view of the internal logics like the decoder and the error handler, and we mathematically prove if they behave securely under all conditions.
The next question is kind of like looking at it from a customer perspective. When evaluating silicon vendors, what key questions should technology decision makers, ask to gauge the maturity of formal verification and other hardware assurance programs?
That's a great question, Jerry. I would start with learning a bit about their secure development lifecycle process. These are the questions I may ask, like what are the key steps and tasks in your SDL? Who owns these steps? What trainings do engineers receive? What methodologies and tools do they use? Which ones find the most issues and why? And what types of issues appear most often? And this is a tricky one, right? How would you remediate security issues when they are found, let's say, 2 weeks before silicon tape in?
Yeah.
And then I would also ask them to focus on maybe formal verification specifically, like which areas use formal for functional correctness versus security assurance, and what tools are they employed? How do you determine which security requirements are formally proven? What is the ratio of security issues found by formal versus traditional testing? And what are the biggest challenges in formal adoption? And these questions should reveal a vendor's investment and capability, and there is no single right answer, but the maturity is often very visible.
Good point. So as platforms evolved, you have more confidential computing instances, more AI accelerators, more disaggregated architectures. How does formal verification need to evolve, and how is Intel preparing for that future?
Yes, there's still significant opportunity to unlock the full potential of formal verification for modern chip design, and we are actively pursuing in multiple areas. And here are 3 that I would like to highlight today. The first one is about AI-assisted requirements definitions. Security requirements written in natural language are often ambiguous, incomplete, or based on hidden assumptions. And rather than relying on experts to spend more time in documentation, we are now leveraging AI to enhance clarity of the specifications and extract high-quality formal requirements. And the second is the tooling scalability. And current tools struggle with very large and complex IPs, and building an abstracted model can take days or even weeks. And to address this, we are working with the ecosystem to drive innovations in more scalable tools and constraint solvers, automated modeling, and property mining techniques. And these advances are essential to make formal verification practical at full SoC scale. And last but not least, holistic hardware firmware verification. And today, hardware and firmware of a platform are verified independently because they rely on different tool chains. It puts much burden on the expert not to miss cross-layer security behaviors. And we are actively collaborating with academia to create some unified verification frameworks to support more complete end-to-end system analysis framework for increasingly complex platforms.
If a customer was to take one message away from the role of formal verification in building trustworthy platforms, what would that be?
I would say formal verification brings mathematically proven assurance to hardware security, and it offers confidence that critical behaviors would hold under all conditions, not just the one that we test. And as system complexities continues to grow, it complements traditional validation by closing the gaps that simulations cannot reach, making it a foundational technique for building trustworthy, high-assurance platforms.
Well, Jason, this is great information. Thank you for joining me today and sharing. To find out more about formal verification, please visit www.intel.com/security report, where you'll find our 2026 Intel Platform Security Report. And I also want to put a plug for N31, our offense security research team. They have blogs, lots of blogs on various verification topics,
including formal verification.
including formal and negative space and a bunch of other stuff where there's a lot of innovation going on there by your team, which is awesome to see. They can be found at intel.com/int31. So again, thank you, Jason, and thank you for watching.
Thank you, Jerry.